Hi, everyone. So the talk is about cost-optimal satellite-assisted video delivery. So the concept is this. There are lots of homes nowadays in the US and all over that have not only wired connection to the internet, but which have also satellite terminals. And they can receive some satellite programming this way, satellite delivered programming. And suppose you are an operator that can deliver content both over OTT and can also work with a satellite company to provision capacity and send data over this link. The question is, can you design the system, hybrid system, in such a way that your cost as a delivery system operator will be lower as opposed to sending it purely over CDN or just sending it all over satellite? So the intuitive answer is probably no, but I thought that this question is quite interesting and decided to look a little bit more on this. And coincidentally, this work is supported by 5G Emerge Consortium, an initiative in Europe looking at creating an ecosystem for satellite-assisted media delivery. So I'm blessed to be supported by this activity. And this is the sketch of a model of a system. And I will approach problem mathematically. You'll see some formulas, but you will see that the problem is actually pretty simple. So there is a satellite chain with a uplink delivering some channels going to players, and there is a parallel link going over CDN, and we could send data either way. In a simplistic way to pose the problem, let's assume that we have n channels and k of them we will send over the satellite, right? And a natural choice of those channels will be, let's pick most popular ones and send over satellite, right? And then the question is, what would be the best capacity or number of channels that we could allocate to support this? So to solve this problem, we need one extra parameter. And this is what is the shape of the distribution, describing pool probabilities for each of these channels. So in this work, I pick as an example zeta distribution. In paper, I actually use generalized zip distribution, which is just a little bit more fancier version of the same. But principle is the same. It's a probability which is monotonic, and I assume that we can always sort the channel such that the first, most popular goes first. And the beauty of this distribution is that we can also produce an analytic approximation of it with a large number of channels such that it becomes a continuous function of parameter k. Again, this is an asymptotic. This is not a discrete kind of definition of it, but if the number of channels is large, that we can rely on this formula. And if we can rely on this formula, and we look a little bit more at the system, and here we will look also at some parameters like rate of encoding of each channel. I assume that each channel has just one single stream at rate R. We look at cost of satellite CDN, total times that was used, number of channels. Then we could easily express the total delivery cost. And it will be average because there is a the probability of X going beyond. So that's a probability of certain number of channels going over CDN versus the rest of them going over satellite. And if we look at this formula for total cost, plug in our asymptotic expression for sort of tail of popularity distributions, we realize that that function now becomes just a function of parameter k, which is now continuous. So we can solve the optimization problem, just produce a derivation and equal it to 0. And here is the formula for the optimal number of channels. It's a closed formula. In paper, I derive it actually for the discrete case with generalized zip distribution, but it's also a simple formula. And from this formula, what we can see, of course, if the number of channels goes up, your number of channels that you need to send over satellites need to go be higher. You need to provision more capacity, right? Depending on the ratio of cost of CDN versus satellites, that will also influences the optimal number of channels. And importantly, most importantly, the shape of your distribution This parameter alpha also influences. The pickier the distribution, the fewer channels you actually need to send over satellite. The more efficient becomes the use of satellite in this case. And of course, there is a break-even point at which you could say that the using of satellite makes sense. Now you can save money. So next is a simple plug-in numbers exercise just to show if that would work in practice. So what I use 120 TV networks, rating numbers published online. I fit it with a zip distribution model, as you could see there, and it fits beautifully with a parameter of alpha, as shown right there. And what I do next, I plug in some numbers. I assume that the cost of CDN, I'm sorry, I'm using publicly placed numbers, not to sort of disclose any proprietary information, which of course is several orders of magnitude different, but let's assume that this is it. Let's also assume that the bandwidth cost is given, and by plugging all these numbers, what we can see that for this particular example, it's about 29 channels that give us the best performance. Well, if I plug all those numbers in that formula, I get a pretty close number. It becomes 29.115, which is good enough. So it sort of works. And what's also important, if you look at sort of this plot that shows the red curve, it's a sum, it's a total cost. And the dotted blue is the cost of the CDN. And the green is the cost of satellite, right? You could see that in the ends, if you move all channels to satellite or all channels to CDNs, the total cost will actually be higher. So we actually do have the minimum point at which this hybrid system performs more efficiently. So that's the essentially main finding here, is that by building the hybrid system and using proper allocation of bandwidth, you could actually make it more cost efficient. You could save some money. Next is the extra twist of the problem, and I will skip some details because it just will be more mathematical. So what if we have a system with two renditions? So in this case, we're dealing not only with probabilities of each channel, right, but also with probabilities of pool of each rendition, right? And we also have two rates. So I'm creating concept of effective bit rate, and so now instead of looking at the distribution of each channel, I'm looking at distribution of each streams in a sense of what's the effective bit rates that they will be pooling, and then I just need to sort this table according that distribution. That becomes a bit more fun. So what we will see here is that effectively what will come up on the top of this table will be interleaved pattern of two renditions corresponding to each channel lineup. And it is possible to estimate the interleave factor at which less sort of popular renditions will be injected in the total mix, and if we know this interleave factor, we can also compute this effective rate for it, and we could effectively pause and solve the problem. So this is just a bit more notations there, but at the end of the route, we also see the formula for optimal number of channels. And it's similar to the previous one. It also has a factor of power of 1 over alpha there. So the same dependencies on the number of channels, on the ratio between CDN and alpha factor. The only extra factor that influences now is the balance between the popularities and rates of each of the renditions. But again, we could make it all mathematical and exactly, and same with any number of renditions. It's just going to be more crazier formulas, but with just a couple more pages, it's all doable. And but bottom line of this is that okay, we know how to allocate, how many channels to allocate to satellite. What else can we say about this problem? Well, there is an extra degree of freedom. If we could influence how many viewers will be looking at rendition 1 versus rendition 2, that might be a factor. And in fact, what this mathematics shows is that the more asymmetric is this distribution, the more streams go to, for example, Ultra HD or Ultra SD, the least impact of this two type of split between of content on two types will have on the capacity. The more effective the use of satellite capacity will be. So if you split, if you decide which rates to allocate, or if you can influence in any other way which streams will be pulled with each probability, creating as asymmetric as possible, that split gives you a key to increasing efficiency of the system. So this is one extra learning from all this exercise. But in the end of it, this is what we can say about this problem. So it's very simple, it's solvable. Mathematically, it's just simple differential equations, nothing fancy. And it shows that these systems could, at least in theory, be more cost efficient. That's important. And we also know that we need to achieve cost efficiency, we need to do the proper challenge allocation, and we need to have a good handle of understanding of what is the shape of popularity distribution as part of it, and a few other parameters. So that's, this is the last slide. So basically there is, of course, it's just a first scratch. There is much more that can be done. And of course, doing something practical will be even more exciting. And looking at other factors that influencing this problem, such as satellites might have different geographic reach, they might be low orbit, they might have floating schedules, and counting this all as part of the factors of the problem. Also throw in geographic sort of distributions of range and other factors that might affect the stability of satellite links or capacity of satellite links. All those things can be added as extra fun components to make it even more exciting to work on in the future as a research problem. But as a practical component here, it looks interesting, I think. Thank you.
Just like I expected, Ben has a question.
Yuri, I'd really enjoy seeing you model out doing the different bit rates on satellite versus terrestrial.
Thank you. Yeah. Well, if you have finite capacity and you need to send a certain mix, and you have reasons to send certain mix, for example, one is HDR, another SDR, then there is no way to around it. Okay. There is one more. Yes.
Hi, Yuri. So this was very interesting. I was going to ask a question by, once you've got the bits onto the satellite receiver, how do you get them into the player? I think that's a complex problem. But then it occurred to me that your analysis here would actually work very nicely if you look at LTE broadcast, right? Because while it's hard to attach the satellite receiver to a player, I can easily put a cellular receiver as a USB device into a TV, and now I can really optimize it. So could you for future work look at LTE broadcast, especially under 5G, and run similar economics?
That is definitely the dimension, and there is also like future 5G. There is MBS, 5G MBS, and there are sort of convergence protocols. Even looking at base stations, satellites as kind of base stations in the sky as extension of terrestrial 5G network. So all these applications are connected, certainly looking at all of this. So that's what consortium is looking at. So I picked one simple kind of theoretical setting of the problem. You could certainly get those signals back if you have a MIBR receiver, for example, MIBR gateway, and you use a MIBR as a way to get a channel signal to satellites. But there are proprietary systems out there as well. And there are companies building hybrid systems by themselves. I'm sure they looked at this problem from their own angle as well. Yes.
Thank you for the presentation. It was great. I guess my question is, as more satellites get sent out into space, mainly by companies like SpaceX, where there's, sending out thousands or tens of thousands of them, have you looked into how to scale that to a future where there's like thousands, if not tens of thousands of these being sent out?
Well, there's certainly a big new phenomena in this market, but they are not the only ones. There are also other operators, traditional satellite operators, and so I'm looking at full spectrum. And there is a merit for using LEO satellites for some applications and GEOs for some others. So it's or MEOs. But certainly. With Starlink, the biggest question I have with them is the moment they will support multicast of any sorts. Right now, it's all unicast, to the best of my understanding. If they will start multicasting, that would be interesting. Because at that point, you could certainly scale up, have more effective distribution. Even within sort of coverage of that satellite, you could reach multiple receivers at that point.
Yeah, Google, thank you. Yeah, this is great.
Thank you.
Hi, it's Keith here. No, Keith.
Yeah.
Have you done just the theoretical study or physical experiment with SES or EURISAT?
So that's members of the consortium. That's what they're working on.
So you are doing the physical one as well, okay? Because they do broadcasting, and then down to the receiver, and then they IP multicast or unicast.
Right. What I present right now is of course just a theory, but there is a work to try to build a real system. And,
Okay, that's the one you mentioned in Berlin. Okay, understand.
All right, thanks to the speaker again.
Thank you.